As discussed in class, this is just a short video that I'm making where I work through several problems of complex capacitors in series and in parallel, both in the same circuit, to give you a sense of what it looks like as someone works through these problems, hopefully to help you see how you can work through these problems yourself. We want to start, of course, by pointing out that we do have our two equations for how to combine capacitors. This is how to combine capacitors in series. This is how to combine capacitors in parallel, but it's a little bit more complex when a circuit has a little bit of both at the same time. For example, this circuit right here, if we were to analyze a circuit, as we get deeper into analyzing circuits, I'll remind you that each battery has a positive terminal and a negative terminal, and we want to analyze a circuit as current flows through the battery and out the positive side. And again, we'll talk more about that as we go through circuit analysis. But as this current comes out of the battery, it comes over here, and the first thing it encounters is this junction or node. So before it hits any actual components in the circuit, it hits a place where the current splits. And so we would trace that there's this path on the left and there's this other path on the right. And they pass through two totally different, separate sets of circuit components. Now, I can see that this is a parallel circuit. I have two different branches, one on the left and one on the right. So I might think, well, I'm going to equation for parallel capacitors, and I might say that the total capacitance is equal to the capacitor on the left plus the capacitor on the right. They're in parallel, so these two branches, so I can just add these two branches together. And that's true, but I don't know what the capacitance value is for the left branch, and I don't know what the capacitance value is for the right branch. So what I would first need to do is add together the capacitors in the left branch here, C1 and C2, which are in series with each other. And then also I would need to find out the capacitance in the right branch. So I would need to say that capacitor 3, capacitor 4 are in series with each other. I need to do these two calculations before I can add the left branch and the right branch. So that's the whole point of these videos, is to sort of walk through the order in which we have to do each of these items. So on the left, I have that capacitor 1 and capacitor 2 are in series with one another. So I would say the capacitance of the left branch will be found with this equation. And as I substitute in my values, I get that the 1 over the capacitance of the left branch equals 1 over 14 microfarads plus 1 over 50 microfarads. And according to my calculator, 1 over 14 plus 1 over 50 equals 0.09. And the units of that will be 1 over microfarads. And this is not what I wanted. This is 1 over the capacitance in the left branch. How do I get the capacitance in the left branch variable out of the denominator? Well, there's several ways you can do this. And you could start talking about, I don't know, cross-multiplying or something. But I think the best thing to do is take your calculator and say that you want to raise this to the -1 power. Because what that does is inverts the value. That brings my capacitance on the left to the numerator, and it makes the right side 1 over 0.09, which comes out to 10.9375, and it makes my units microfarads instead of 1 over microfarads. So that's the capacitance in the left. I will find the capacitance in the right branch the exact same way, using the values for capacitor 3 and capacitor 4. And being careful with my calculator. And I remind you, I'm not worrying anything about a common denominator or anything. I'm doing the math with my calculator. Although there is always a danger that if you do too much of the work with the calculator and don't show enough of your work, then the person grading your work won't know how you got what you got, which in this case is 48.96 microfarads. Which means I can now add the left and the right values, just adding them together because they're two parallel branches, gives me that this entire circuit has a total capacitance of 59.9 microfarads. And each step of that is really pretty easy. The hard part is it takes a little bit of practice to know and to have some confidence what order the steps need to come in. So again, I'll do a few more here. In this circuit, I have the battery, and I have the first thing I encounter is capacitor 1. It is in series with everything else in this circuit. And then we run into our first node or junction or intersection. And we see that capacitor 2 and capacitor 3 are in parallel with each other, meaning that the current or the trace from the positive end of the battery to the negative could go through one or the other, but you won't go through both in a single unbroken trace as you run your hand around from the positive to the negative. You would either go through C2 or C3. So C1 and C4 are in series with the parallel branches C2 and C3. So the first thing I have to do is find out what the total capacitance of C2 in parallel with C3 is. I just add them together, and I get that the total capacitance for that region is 234 microfarads. Now I can add that 234 microfarads in series with capacitor 1 and capacitor 4 to find the total capacitance of this entire circuit. Being careful to use the correct equation, of course. And I get that 1 over the series capacitance is equal to 0.0272965. It's running on. But again, if I take that whole thing to the -1 power, I will invert that and find that this entire circuit has a total capacitance of 36.6 microfarads. So if you haven't been with the previous two, I'd like to encourage you for this one and the following ones to pause the video and see how far you can get working it out, and hopefully you'll have an answer, and even better would be if we get the same answer. Okay, I see that this circuit is actually very similar to the last one. It's just turned 90 degrees, but I'm going to have the current come out and encounter one capacitor, then encounter a parallel group, and then another capacitor in series. So my first and last capacitors are in series with that parallel group. So just as in the previous video, I need to find what this parallel group total capacitance or equivalent capacitance is first, which thankfully is pretty easy. And then once I know that, I get to add that in series with the other two capacitors to find the total. And so when you do the math on this, of course, want to be careful to actually invert it at the end. Your answer should not be 1 over the series capacitance, but rather the series capacitance itself. So always have to remember to get that variable out of the denominator when you're done. One of the things I don't really like, but it does come up, is a question that is presented in a way that is kind of meant to be tricky. So if I'm trying to find, for example, as I trace through here, this circuit is drawn to be a little confusing because I can see that C1 and C3 appear to be in series with each other, but there's this parallel thing going on with capacitor 2 that's in parallel with C1 but not with anything else, and then C4 is in parallel with C3 but not with anything else. And that might not be confusing to you, but to a lot of people it is. And anytime you find a circuit that is set up, you're looking at it and it seems confusing, I find it can be really useful to redraw it with something that you are sure is equivalent. For example, I know that capacitor 2 and capacitor 1 are definitely in parallel with each other. I know that for sure. And I know that there's nothing else in series or parallel with either of them between this node and this node. So that becomes this node and this node. If this redrawing doesn't seem to be helpful to you, that's fine. But where this becomes helpful to some people is that between this node and this node, I can see nothing is happening except that C3 and C4 are parallel with each other. So I can now say that I have a parallel C3 with C4, and this is a slightly different looking circuit, but it actually means the exact same thing, and that may help streamline your thought process on certain circuits. For example, I now know that as I move from left to right, I have a total capacitance will be in series because I have I guess group 1, let me call that, I can't call it 1, group A, plus group B, where A and B are the first and second combinations in parallel. So capacitor A would be the equivalent of capacitor 2 plus capacitor 1. So 600 picofarads, because they're in parallel, I just get to add them. And then capacitor B is what I've decided to call that second grouping of capacitor 3 plus capacitor 4. And again, since they're in parallel, I can just add them to each other. I can say that that comes out to 1,000 picofarads. And now I can say that the 600 picofarads and the 1,000 picofarads are in series with one another. And I get, therefore, that the total capacitance of this circuit is 375 picofarads. I hope you're getting the same thing. If you're not, of course, try to find exactly where we're disagreeing and let me know. I like this one because this looks complicated, but if you've done even a few, you can look at a circuit like this and say really quickly, these three are definitely in series with one another, and so I'll need to find out what's going on with them with the series equation. These two are in parallel with each other, so I'll have to find out what's going on with them in a parallel equation. Also, these two are in parallel with each other, so I'll have to find out what's going on with them with the parallel equation. And of course, those two that I have highlighted in blue in parallel, we can add together very quickly. These two in green as well, because they're in parallel. And these three in red, even though they're in series, so I don't maybe trust myself to do the math in my head as well, I can still do them pretty quickly with a calculator. Although I'll admit, in this case, it seemed a little tricky. I don't want to make that seem like it was a big deal, but having 1 inverted and become 1 microfarad would be a good spot to stop and make sure that I'm doing that correctly. Now that I've established that I can simplify a couple of these sections, let me show you what this entire equation really ends up looking a lot like at this point. It looks like this. I've just redrawn the circuit, and it looks a lot less complicated now. This looks like 4 capacitors. And that's really the whole point of how we deal with more complicated circuits like this, is we take what we know how to reduce and combine, and we do so. Suddenly the circuit starts to look much more manageable. So in this right branch, if I combine these two, I get that the right branch has 2 in series that come out to an equivalent of 3 microfarads. And I now have a 3 microfarad in parallel with a 1 microfarad, and the 10 microfarad is in series with that parallel grouping. So again, I've got that the 1 microfarad red plus the 3 microfarads that represents the leftmost branch. That's a total of 4 microfarads, and 4 microfarads is in series with that 10 microfarads, which if we run through the series equation and we're careful, we should wind up with the total equivalent capacitance in this one coming out to, I get 2.857 microfarads. I'm showing you this circuit, even though I said this is more complicated than what I would expect you to be able to do back for me. If I'm going to maybe ask you to do 3, 4 capacitors at a time, maybe 5 capacitors at the most, the reason I would want to show you one that's more complicated like this is to emphasize that it really is the same rules, and it would just take more steps, which does introduce more opportunities for mistakes. But if we're cautious with it, it's just more steps of the same nature. And let's be clear, that's why I don't feel it's necessary to ask you questions like this on a test. If you can do a problem that has 4 capacitors, then to me that shows that you know how to do one that has 8 or 12 or 20. We don't need to ask you to do the most complex one possible. Of course, one of the things that can happen that will seem a little weird sometimes is if you do a complicated circuit, then afterwards, sometimes one that you know isn't as complicated just looks weird, and it can be a struggle to try to trace your way through and figure out what's going on. But I really find it's useful to go step by step and say, I can identify that this is a parallel grouping, and I can identify that this is a parallel grouping. And then I can actually redraw the circuit so that it looks more simplistic and more manageable. And so now, even if I'm not showing all of my steps and I'm sort of skipping some, you can tell what it is that I'm doing because I have redrawn the circuit and then done some calculations separately over here. The blue and yellow writing is completely separate from the original drawing, so you can tell what that's supposed to go to. And I get, by the way, that the total capacitance of this whole circuit comes out to 6 microfarads. I hope you did too. This is another one where I think it can look really tricky when you first look at it, and I'd like to encourage you to try to redraw this to be something equivalent and maybe less confusing. If you don't find this confusing, that's awesome, but again, a lot of people look at this and just find it to be a little bit confusing. Try redrawing it. If you need a hint, I will tell you to focus on what's going on between this node and this node, these 2 red nodes. And I will draw my version of this circuit over on the right here. There, and we can see this means the same thing because from the red node to the other red node, I could either pass through the 1 capacitor or I could pass through a series of 3. Over here on my drawing, it shows the exact same thing. I could go through 1 or I could go through a series of 3. So if they mean the same thing, why would I redraw it? Oh, that was terrible. I would redraw it because the one on the right, to me, makes a lot more sense. Just visually, I look at it and I understand what's happening. So it seems easier for me to deal with. On this one, other than redrawing it, I'm going to skip all of my calculation work and just show you what I get for the answer. So again, pause this and see if you can work it through if you're looking for the extra practice, and then we'll see if you get what I get, which is 129 nanofarads. And after I built it up like that, I sure hope I got the right answer. That's all the ones I wanted to share this time. Again, if you're struggling with these, don't feel like we're in a rush, and you can always come in and get some help during office hours or stop by the SMLC. The tutors there are fantastic.